Okay, so we're going to begin chapter 7, continuous probability distributions and the normal distribution. Now, chapter 7 is a very, very, very important chapter. Not like the other chapters weren't important, but this really is going to be the foundation for the rest of the chapters. So it's really, really important that you get a good grasp of the information that's in chapter 7. So I want to start off by going over an example that should look familiar to you, and I'm going to kind of tie it into where we're going. So in chapter 6, we learned all about discrete probability distributions. So we were working with discrete random variables, right? Random variables that had a countable number of values. And one of the things that we were able to create was a discrete probability distribution histogram. So I have a probability histogram right here, and X represents the number of correct answers. Let's say that somebody, gets on a test. So we have the probability on the vertical axis, and X on the bottom is the number of correct answers. And it looks like it got misaligned a little bit. So the first rectangle should have a 0 under it. 1 is under the next rectangle. 2 is under this rectangle, so on and so forth. It looks like it just got a little shifted. So let's answer the first question. So the first question says, what is the probability of getting one correct answer? So I'm right here. So if we look at X, the number of correct answers on the bottom, if we look at 1, we're going to see, if we shade this rectangle, that the height is 0.3955. So that's going to be the probability of getting one correct answer. So 0.3955. No big deal, right? We've read and looked at these discrete probability distributions before. So let's look at question 2. What is the area of this rectangle? So that's a little weird, right? A little bit different. We haven't answered a question where we had to find area, but I'm going to make a connection between probability and area. So just go with me with this. So you guys know area, right? Area of a rectangle is equal to length times width. So the area of this rectangle that I have shaded, well, the width, the bottom, is equal to 1 unit. So it's 1 unit across. And then the height, right, or the length is 0.3955. So the area of this rectangle, length times width, is going to be 0.3955 times 1, which is just 0.3955. So that's also the area of this shaded rectangle. Let's look at question 3. What is the probability of getting 1 or 2 correct answers? So let's cross this out. Now, 1 or 2 are going to be these shaded rectangles, right? So this is x equals 1. The second one that I shaded is x equals 2. So we're going to add the two probabilities together, right? So the height of the taller rectangle is 0.3955. And then the height of the next rectangle is 0.2637. So we're going to add 0.3955 plus 0.2637. So let's add that together, 0.3955 plus 0.2637, and we get 0.6592. So 0.6592 is the probability of getting 1 or 2 correct answers. So now I'm going to go back to the similar question that I asked you before. What are the areas of these rectangles? So what's the total area now in these shaded rectangles? Well, we know the area of the first rectangle because we just did it in part 2, right? So the area of the first rectangle is 0.3955. Now the area of the second rectangle is length times width. So the width again is 1 unit and the height is 0.2637. So it's going to be 0.2637 times 1. And we get 0.2637. And we already said when we add 0.3955, so the area of the first rectangle, and if we add the area of the second rectangle, we get 0.6592. And then let's answer one more question, and then we'll kind of cover the relationship that I'm trying to have you guys see. So what if we were to take the area of the sum of all the rectangles? Well, we would take the probability, right? So the height of each rectangle we're seeing is that it's equal to its probability, right? And the width of each rectangle is just 1. So we would just need to add up all these probabilities, right? To add up all the areas of these rectangles. And I'm not going to do it because we already know, based on what we learned in chapter 6, right, the properties of a discrete probability distribution. What should the sum of all the probabilities be in a discrete probability distribution? It should add up to 1, right? So if you were to add up those numbers, we are going to get 1. So now my point is, what is the relationship between area and probability? Well, what I wanted you guys to see from this example is that, look at 1 and 2. The area in part 1 is equal, or I'm sorry, the probability in part 1 is equal to the area in part 2, right? And then for 3 and 4, the area of these two rectangles is equal to the probability, right? The sum of the probability of these two rectangles. So what I want you to realize is that the area of the rectangle is equal to probability. This is going to be very useful to us. So let's keep that in mind. The area of a rectangle is equal to probability. So let's look at 7.2 here, continuous probability distributions. So in chapter 6, we only dealt with discrete probability distributions, right? And binomial distribution, which was also a discrete probability distribution. Now we're going to move into probability distributions for continuous random variables. So let's look at an example first. So let this continuous random variable x represent the amount of time a college student needs to travel between classes at NCC. The amount of time is recorded to the nearest minute for up to a maximum time of 20 minutes. Now, I notice here, look at all these heights of these bars are all the same, right? Because these are kind of like all the late kids, right? So there's 15 minutes in between classes, because this is measuring the amount of time it takes to travel between classes. And you have 15 minutes in between classes. So these extreme values here are kind of the late students. I don't really want to look at them for now. Let's just assume we have this bell-shaped distribution here for time, right? So we've seen this shape before. This is symmetric or bell-shaped, right? So how do we read this table, right? This histogram. So there's a rectangle associated for each minute to get to class. Now we know that area equals probability. So the area of each rectangle represents the probability that the student will take X minutes to get to the next class. So for example, what is the probability that it takes a student 10 minutes to get to class? Well, let's look at the horizontal axis because that represents minutes, right? Let's go to 10 minutes. And if we look at the height of the rectangle or the area of the rectangle, it's 0.06, right? Because its height is 0.06 and its width is 1 minute, and 0.06 times 1 is 0.06. So remember what I said up here. The area of a rectangle is equal to the probability. So in this case, the probability that the time it takes to get to class is 10 minutes, that's going to be equal to 0.06 or 6%. So there's a 6% chance that it's going to take a student 6 minutes to get to their next class. So here I say the area of the rectangle for x equals 10 is equal to the probability that it takes a student 10 minutes to get to class. And again, here I'm reinforcing that the area of a rectangle is equal to probability. So without even adding them all up, what will the sum of the area of all the rectangles of this histogram equal? So if I were to add up all the probabilities underneath this, that are associated with each rectangle in this histogram, they're going to sum up to 1, right? All the probabilities in a probability distribution should sum up to 1. And I'm not going to do it, but you could check on your own, add all those up, and it's going to equal 1. So what happens, because remember, time is continuous. Now, what's significant about a continuous variable? Think about it. What was the difference between discrete versus continuous? We learned this in chapter 2, and then I went through the difference again at the beginning of chapter 6. So a discrete variable takes on a countable number of values. A continuous random variable takes on an infinite or an uncountable amount of values. So time is continuous, right? Now we broke time into minutes in this first graph, 1 minute, 2 minute, 3 minute, 4 minute, all the way up to 20 minutes. But what if we wanted to break time into quarters? So for example, what if we listed time as 1.25 minutes, 1.5, 1.75 minutes, and so on and so forth? What happens? There's a lot more rectangles, right, than in the previous diagram. And I want to show you something else in this first diagram that we looked at. Again, I'm just going to ignore all the late people for a minute. If we look at this bell-shaped symmetric curve, let's trace it and let's try to get as close as we can to these bars. We're not going to be able to fill in all the space, right? See all this empty white space here that I'm filling in with my yellow highlighter, right? This is like empty space. I want you to see what happens to that empty space when we change the units from minutes now into quarters of a minute, right? So, I mean, we're still in minutes, but we're breaking it down even further to quarters, right? Look at this. We have so many more rectangles in figure 7.2b than we did in the figure above. And again, if we ignore the late people and we look at this bell-shaped curve, look at how much closer now I could get to this smooth bell-shaped curve when I trace it. And you see, if I go to fill in the empty spots, there's a lot less room. There's a lot less space, right, now to fill in than there was in the diagram above, because we have so many more rectangles now, right? But regardless of how we broke down time, time is still continuous. And the sum of all the areas of the rectangles equals the sum of the probabilities. That's still going to be 1. So if I were to add up all the probabilities in this distribution, they're still going to add up to 1. And for example, if I wanted to calculate the time that it takes a student to get to class, right? So the probability that it takes from 5 to 7 minutes, I would look between 5 and 7, and I would get the area, the shaded area, right, of these rectangles. So I'm still going to get my probability answers the same way, right? I need to know the area of the rectangles. But as we break down time to a finer degree, so for example, we could break down time into tenths. So we could go 5, 5.1, 5.2, 5.3. Then my rectangles are going to be even thinner and I'm going to have more of them. I could break down time into thousandths of a minute and so on and so forth. So as the rectangles get more frequent and narrower, eventually we're just going to get a smooth curve, and there's not going to be any space, any of that extra white space, right, underneath this curve. So this would be an example of a smooth curve if we were to not, if we were to just break down these rectangles finer and finer and finer and finer until we couldn't see rectangles anymore. And this is called a probability density curve. And this represents a continuous variable, particularly time in this case. And if we wanted to know the probability that it takes a student between 5 and 7 minutes, what's the probability that it takes a student between 5 and 7 minutes to get the class, we would need to figure out what the shaded area is underneath this smooth density curve. But how do we do that? Because these aren't rectangles, right? This shape that I just shaded in blue is not a rectangle. You see how it almost is like a rectangle, right? But then it has a little bit of extra area on top. So we have a table. So a mathematician created a table that's going to have any area that we want to look up under one of these bell-shaped symmetric curves. And these areas are all based on calculus. So some of you might have taken calculus before and you remember how to find the area under a curve. If you didn't, that's fine. I'm going to teach you how to use this specific table in order to find an area under the curve. So from now on, these nice, smooth, continuous density curves, we're going to call them normal distributions. So we're used to calling them bell-shaped symmetric, but now I'm going to call this a normal curve or a normal distribution, which is the same thing as bell-shaped symmetric. And what we're going to do in the next lesson is I'm going to teach you how to use this table of areas to find an area under the smooth density curve called the normal distribution. So what I want you to do in the meantime is I want you to read over the characteristics of these continuous probability distributions. And then we're going to talk about the normal distribution. And then I'm going to show you how to use the normal table. So in the next lesson, I'm going to show you guys how to calculate areas under the normal distribution.